Okay, great. I hope you can hear me all today in this very busy pavilion. It's great to be here to say a little bit about some of the research that's been going on around ice sheet dynamics and sea level rise, with a particular focus on some of the latest science that's been published since the last IPCC report. What I'd like to cover in the next 25 minutes or so are, first of all, some lessons from the past. So whilst a lot of my research at the moment focuses on modern day ice sheet dynamics, I do have a background in paleo ice sheet dynamics, and I think there are some really important lessons about how ice sheets have behaved in the past that can tell us about likely future scenarios. And then I'm just going to skip through some recent observations of the Greenland ice sheets and of the Antarctic ice sheet. And those numbers in brackets there, 7.2 meters alongside Greenland and 57.5 meters alongside Antarctica, that's the amount of water in sea level equivalent that these ice sheets currently store. So you can imagine that even 5 to 10% change in their volume, we're talking several meters of sea level rise. And this is why, when you're thinking about sea level and sea level rise projections, we really need to be looking at some of the big ice sheets in Greenland and Antarctica. And then I'll finish by looking at some projections of future sea level rise, and then finish with some conclusions before I invite Kim Ross up, who's going to say a little bit about climate change impacts, particularly from Florida. So first of all, one of the first lessons, and there are 3 of these lessons that I want to go through. One of the first lessons that the past ice sheet behavior tells us is that ice sheets are sensitive to temperature thresholds, and that once those thresholds are crossed, we can often see irreversible sea level rise. So it's quite a complicated graph on the bottom left-hand corner there, but I don't want you to take in all of that information. Just focus on the scale on the bottom there. We're going from 0 to about 14 degrees of warming. And on the left-hand axis, you've got the ice sheet volume in meters of sea level equivalent. And currently we're at about 1.2 degrees of warming. So you can see kind of where we are. And if you look at the top red line there, we're kind of on a flat line. And as we increase temperature, you can see that there's not much of a change. Gradually increased temperature, there's not much of a change. But then there becomes a point where that curve starts to dip strongly downwards. And that's when ice sheet mass change becomes irreversible. And at that point, there's very little we can do to stop it. Okay, so it's really important from a kind of global warming perspective that we stay below that point beyond which ice sheet loss becomes irreversible. And the reason for that is that once you exceed a certain elevation, a certain temperature threshold, we get what's called ice sheet instabilities. And I'll say a little bit more about those later in the talk. But for now, I just want you to look at that model simulation on the right-hand side, showing you what happens to Antarctica as you increase sea level. And what you kind of see on that simulation is that you see quite rapid jumps in the mass change. It's not a linear, gradual process. There are times when all of a sudden things start to really step back, particularly in parts of the ice sheet that rest on a bed below sea level. And I'll say a bit more about that later in the talk as well. But the key point here is that when you increase temperature, you will start to see some changes in ice sheets that become unpredictable and irreversible over very short timescales. And here we're talking about a few centuries. I should also point out that the thresholds that were on this paper as recently as 2020 have already been lowered. So we used to think that the West Antarctic threshold may have been maybe over 2 degrees. We used to think that East Antarctic ice sheet, well, you can see there, somewhere between 6 and 8 degrees. In fact, it wasn't that long ago that we thought the East Antarctic ice sheet would be immune to climate change unless we warmed by 17 degrees. But we now know that those temperature thresholds have lowered quite substantially over the last few years. And again, I'll conclude with what I think the latest thinking is there. The other really important lesson then from ice sheets in the past is that sea level rise has been 10 times faster than current rates. You're seeing a simulation there of the relatively slow deglaciation of the North American ice sheet during the last ice age. And you can see on the right-hand plot, on the bottom axis, thousands of years before present, around 21,000 years ago, sea level was about 140 meters lower than present. But as this ice sheet deglaciated, sea level rose, but it didn't rise in a steady, consistent fashion. Rather, there were jumps in sea level. There's one labeled on the graph there about 14,000 years ago called meltwater pulse 1A. And during that period, we saw 4 meters of sea level rise per century for a couple of centuries. These are rates that are 10 times faster than present. So this tells us relatively small changes in temperature will lead to very, very fast rates of sea level rise. And then the final lesson from the past is that when we look at past warm periods, we see situations with temperatures very similar to today, perhaps just slightly warmer, when sea level was much, much higher. So what you can see on this plot here, and it is quite difficult to understand, but again, on the bottom axis, we've got the global surface temperature, the peak global surface temperature. And on the left-hand side, we've got global mean sea level rise. If I just highlight this little box here, what this shows you is, if you hold temperature at 1.5 degrees for 2,000 years, you are committing 2 to 3 meters to sea level rise. So even if we hold temperatures now at 1.2 degrees of warming, we are already committing maybe 1 to 2 meters of sea level rise, but it will be slow and steady, potentially much easier to adapt to. If you hold temperature to 1.5 for maybe a longer period, so the purple bars are showing you for a 10,000 year period, you see that we could get 25 meters at 3 degrees. Yeah, okay, so you can see there on the graph, that bar there, if you hold Earth's temperature for 3 degrees, past records show that you get about 25 meters of sea level rise, which is catastrophic. However, what we're really worried about now, and the IPCC have been very clear about this, is that ice sheet instabilities could be triggered somewhere between 1.2, 1.5 and 2 degrees. So this graph here is kind of showing you the long-term commitment if you hold temperatures for thousands of years. But if we exceed those temperature thresholds that I just talked about, you'll start to see sea level rise rapidly accelerate. And that's what we're really worried about. And that's what the focus of the rest of this talk will be on. And I should say as well that some scientists think that some of those instabilities may already be underway now. And it's fair to say that if they are, we probably won't know for another few decades. Okay, we won't know until it's too late. So I'll just try to take you through some observations of measurements of the Greenland ice sheet. So in Greenland, remember, it contains about just over 7 meters of sea level equivalent. So if this ice sheet disappears, we see 7 meters of sea level rise. The mass is gained by a snowfall each winter, and then the mass is lost largely during the summer through surface melting. The ice at the surface of the ice sheet melts, but also what you can see on this map are those red areas where we have ice flowing, carrying ice from the interior towards the ocean, breaking off as icebergs. And that also contributes to mass loss and adds to sea level rise. An example of that in this animation here is one of the fastest flowing glaciers in the world in West Greenland. This glacier has flowed at up to 14,000 meters per year. And it's an iceberg factory. You can get an impression here of this animation of it pulling down ice from the interior, discharging it into the oceans. And what we know from our measurements of the Greenland ice sheet is that the mass loss, the melting, the discharge, far exceeds the mass gain. And there's been a large increase in surface melting in particular. And this is due to a process known as Arctic amplification, where the Arctic is warming 4 times faster than the global average. So we'd expect them to be more melting in Greenland. Here's an example of a typical season through the summer. The blue line, if you like, with that grey shading either side of it, shows you a typical melt extent on the Greenland ice sheet. If you look at the 2023 melt percentage, it was almost triple that for the summer months in July and August. And this is an increasing trend where we're seeing more and more of the surface of the Greenland ice sheet melting. In fact, some people think that this ice sheet now is kind of catching up with climate. We're already committing about 27 centimeters of sea level rise just as the ice sheet re-equilibrates with today's climate. So this is really worrying. It's like when you take a big block of ice out of the fridge, it will take time to melt. And this is what we're observing with Greenland. It's catching up with the climate, whilst the climate is also warming at the same time. In the one sense, I'm sometimes optimistic when we look at the mass balance records that we see this ice sheet was actually in balance as recently as the early 1990s. That's when the mass gain from snowfall was approximately the same as the mass loss. And at that time, CO2 was about 350 parts per million, and global warming was about 0.8 degrees above pre-industrial. And of course, those values have increased, which is very worrying. And as a result of those changes, Greenland ice sheet has lost 3,900 billion tons of ice over the last few decades. And that alone has contributed 11 millimeters to sea level rise. That's the blue line that you can see there. And the other 2 lines are showing you that proportion from the surface melting and the proportion from the dynamic discharge or the ice flow. If we look on this animation now, this is satellite observations that measure the weight of the ice sheet. So you can see each winter that upticks in the yellow line, that's when it gains mass, and then each summer it loses mass. And the animation on the left is showing you where on the ice sheet they're losing mass. And you can see those yellow and red colours there, showing you that most of this ice sheet is losing mass around the margins. And on average, this ice sheet has contributed about 0.7 millimeters per year. I just want you to keep that number in mind. So between 2007 and 2018, the processes that you're observing in this animation added about 0.7 millimeters to global mean sea level, just from the Greenland ice sheet. We're not talking about mountain glaciers or Antarctica. This is just the Greenland ice sheet. But if we look at the really recent observations, that 0.7 has increased to 1.1. The latest kind of estimates of this ice sheet show that we're now seeing Greenland contribute over 1 millimeter to sea level every year. And again, what's significant about that is that when the IPCC projected mass loss for Greenland over the next decade, this observation sits at the very upper end of that. So it's almost worst case scenario as was predicted in the IPCC report. And if this continues just on a linear track, we'll see 20 centimeters added to sea level by the end of this century. But of course, this probably isn't linear, it's probably accelerating, and that number will go up. Just on my final slide on Greenland, I just want to look a little bit further into the future. There has been some modeling done using different emissions trajectories from low end, RCP 2.6, medium 4.5, and a high emissions is 8.5. And these projections of sea level rise go out to the year 3000. And what you can see here is that under a low emission scenario, we're probably looking somewhere between 1 and 2 meters of sea level rise just from Greenland. Under a high emission scenario, we almost lose the whole ice sheet within a couple of millennia. So again, this ice sheet is very, very sensitive. One of the things we're particularly worried about in Greenland is what we call a surface elevation and melt feedback. This is a self-reinforcing feedback. It's one of those instabilities I mentioned earlier, whereby once it starts, it's very difficult to stop. Because you have an ice sheet that's high up in the atmosphere, you warm the climate, you melt the surface of the ice sheet, which causes it to lower, it brings it down in altitude to a warmer elevation, that causes more melting, that leads it to thin even further, and we just keep lowering the ice sheet in this kind of runaway feedback. This is something we're really worried about, because we used to estimate that the threshold for this process was probably just over 3 degrees. That was in a paper in 2006. More recent work lowered that to 1.6 degrees. And very recently, some people have said it's probably about plus 1.5. Now, we have to be a bit cautious interpreting these numbers because we don't know exactly, and there is some uncertainty. But the key message here is that those threshold temperatures are being lowered by scientists every few years. And this is very worrying. And again, there are some scientists and papers in the peer-reviewed literature which suggest that this process is actually initiated already in parts of Greenland. Okay, I'm going to move to the southern hemisphere now and just say a little bit about Antarctica. First thing to say about Antarctica is that we often separate Antarctica into the East Antarctic ice sheet and the West Antarctic ice sheet. And I kind of draw around the East Antarctic ice sheet there because it's by far the largest ice sheet on Earth. It contains over 50 meters of sea level equivalent, whereas West Antarctica is about a tenth of that. Again, mass is gained in Antarctica via snowfall, but unlike Greenland, there's very little surface melting. So most of the mass lost from Antarctica is through what we call that flow, that dynamic discharge, where outlet glaciers are pulling ice down and they're carving icebergs into the ocean, and that contributes to sea level rise. And what we've observed, particularly around parts of West Antarctica, is that warm ocean currents are creeping under the margins of the ice sheet that are floating. They're melting them, they're weakening them, and that's causing the ice to flow more quickly into the ocean. So we know in West Antarctica that those mass loss processes now far exceed the mass gains. The East Antarctic ice sheet, if there's one piece of good news in this talk today, seems to be just about in balance, but there are some worrying signs from some parts of East Antarctica, particularly a basin called Wilkes Land, which I've highlighted on the map there, and I'll draw your attention to that in the next couple of slides. So this is showing all of the ice sheets now. The blue line is Greenland, which I showed a few minutes ago. The West Antarctic ice sheet is the kind of dark blue with the Antarctic contribution as a whole in pink, so they track each other because most of the mass loss is from West Antarctica. And then the yellowy orange line at the top is East Antarctica, which so far seems to be in balance. The small red line is the Antarctic Peninsula, which is a small peninsula that hooks up towards South America. And that's also losing mass, but there's not as much ice in that part of Antarctica. So West Antarctic ice sheet has contributed about 7 millimeters to global mean sea level rise. That figure for Greenland was 11, West Antarctica 7. Again, if we look at an animation of the Antarctic ice sheet, we don't see the seasonal fluctuation so clearly because there's much more variability in the amount of snow that falls each winter, and that masks the picture somewhat. But what you can see here, over this time period, the Antarctic ice sheet as a whole has contributed about 0.4 millimeters to sea level rise, but most of that mass loss, those orange and red colors, are sourced from the West Antarctic ice sheet. But as you can see, as we get through this animation, particularly in the last decade or so, notice that hot spot appearing on the bottom right of the map. That's Wilkes Land. That is a part of East Antarctica now that we're starting to get quite worried about because it seems to be responding in the same way that the West Antarctic ice sheet was 2 or 3 decades ago. We're seeing the emerging signs of mass loss in East Antarctica, and this is very worrying. The small animation here, just to give you a feel for the kind of processes we're seeing in West Antarctica. This is Pine Island Glacier. It's about 25 kilometers wide. It's a huge glacier. And you can see here that the floating tongue keeps breaking icebergs off. It's getting warm ocean currents underneath it. It's causing it to retreat and thin and increase discharge. I mentioned Wilkes Land, and I'll just draw attention to it on one slide, because what we've observed in Wilkes Land are the emerging signs of mass loss. The rate of loss is now 10 times higher than it was just a decade ago, albeit from a low baseline. And if we look at the ocean temperatures offshore Wilkes Land, they've also increased to up to 2 degrees. So again, it's ocean warming that is driving these processes. And actually, if you were to look at the whole of Antarctica, the third fastest rate of retreat now is this a particular glacier in Wilkes Land, which is almost as fast as what we call the Doomsday Glacier in West Antarctica. Before I look at sea level rise in a bit more detail and some of the projections, just I want to explain two processes that we're particularly worried about in Antarctica. These are what we call instabilities that lead to that irreversible retreat, which I mentioned earlier. The first of these is marine ice sheet instability. And this occurs when we have an ice sheet resting on a bed or land that's below sea level, but it deepens as you go inland. So what that means is that if you trigger an initial retreat, you increase the cross-sectional area of the ice sheet, and it forces it to discharge more ice. And we've known about this instability for quite a long time, and it's theoretically robust. The equations have been written, they've been put into numerical models. We know it can happen. Some people are suggesting that it's already underway. Even 10 years ago, people have said that this marine ice sheet instability in West Antarctica has begun, and there's nothing we can do to stop it. There's other recent papers suggesting that it's perhaps not quite started. But the key thing about these recent papers was that if you just hold climate at present day, that alone, if sustained, even without further warming, leads to marine ice sheet instability, which happens to then contribute about 3 to 3.5 meters to sea level rise. So that's really worrying. The other instability that I'm just going to mention briefly is the marine ice cliff instability. This has been suggested to be important much more recently. And this is where you have a floating part of the ice sheet, and perhaps it collapses very rapidly. Perhaps there's some meltwater on the surface, it fractures apart the floating ice shelf, and that platform disappears, and it exposes a cliff at the grounding line or in the margin in deep water. And that cliff then effectively just collapses into the ocean, much like a coastal cliff would. So this process is something that's been suggested more recently. It's been plugged into some of the models. We know it's not yet underway. There's no observations of this process happening at present, at least on a large scale in Antarctica, but it's certainly plausible if we start to remove those floating ice shelves. And modeling shows that if you incorporate this particular process, this ice cliff instability, we get really catastrophic rates of sea level rise. So although there's only a few papers that have built this into their models, the IPCC did take this seriously, and they said they were unable to rule out some of the projections incorporating this process that could see 15 meters of sea level rise by 2300. So this is one of those models that's using the instability, the marine ice cliff instability. And you can see here, top left, this is the rate of sea level rise in blue, or the total sea level rise in blue, I should say, through to 2100. And with warming limited to 1.5, we see that we get a small amount, maybe just 10 centimeters by the end of the century, maybe just 1 meter by 2300. Something that potentially we can adapt to. But if we increase temperatures bottom left to 3 degrees, we start to now look at maybe 1.5 meters by 2300, and then 10 meters or more under a high emission scenario. Then you can see that on the right hand side. So what we're saying here is that keeping warming to 1.5 will really limit the amount of ice lost, we hope. Best case scenario. But if we go above 1.5, certainly if we start heading towards 2 to 3 degrees, and 3 degrees, of course, is where our national determined contributions takes us at the moment, we start to see catastrophic sea level rise when these processes are incorporated. So the IPCC were very clear that projections in which Antarctica contributes much more than the kind of assessed ranges, the likely ranges under high emissions, cannot be ruled out. That's something like 7 to 14 meters. What's often lost on this graph on the right-hand side, which shows the projections for 2300, is that even a relatively low emission scenario, SSP1 2.6, sees over 3 meters by 2300. Even a relatively low emission scenario. That's why 1.5 is so important. Here's a slide showing the very latest paper on global mean sea level rise, which has now doubled over the last few decades to 4.5 millimeters per year. And we know that in terms of the contributions from Greenland and Antarctica have quadrupled since the 1990s, since they were last in balance. And it appears to be accelerating. Another point just to mention is that when we look at sea level trends globally, that number, if it's 1 meter or 3 meters, for example, that's not felt equally around the ocean surface. There are processes like winds, like upwelling, ocean temperatures that actually lead to variability. So on the axis there, I've showed you where 4.7 millimeters per year would sit, but anything above that in red and darker oranges shows you where sea level rise is even higher. And some places might be feeling sea level rise that's approaching 7.5, 8 millimeters per year due to local effects. I think that's really important to remember. And of course, these figures for global mean sea level, they do not incorporate things like storm surges and other events, which are all magnified by sea level rise. And just to end now with a few maps of coastal inundation from these sea level rise projections. So for context, 230 million people live within a meter of sea level rise, 1 billion people within 10 meters. That shows you how many people might be affected by some of these rates of sea level rise. 20 centimeters of sea level rise has been estimated to cost US $1 trillion for the world's 136 largest coastal cities. The map that I showed you here, which is from kind of my part of the world in northwestern Europe, 0.7 meters is the likely range for an intermediate emission scenario, so about 2.7 degrees. So this is something that's kind of very, very plausible, and you can see here what's happening. In fact, it's already happening. This is from the east coast of the UK, where you can see where cliff erosion is really posing some serious challenges. But we could go to other parts of the world as well. Again, an IPCC quote, global mean sea level rise approaching 5 meters by 2150 under high emissions cannot be ruled out. And the map here shows areas inundated. Florida, Kim's going to say a bit more about this in a few minutes at the end of the talk. I've picked some other parts of the world here as well that you might recognize. But in Brazil, next year's host for COP, of course, again with 5 meters of sea level rise. West Africa, we have other parts of the world, Papua New Guinea, Pacific Islands in particular, vulnerable to sea level rise. This is why we talk about an existential threat. These whole islands will be underwater with some of these sea level rise projections. And again, this is China and Shanghai, in this case, shown on the map. So to conclude, ice sheets were last in balance in the 1990s, when temperatures were just 0.8 warming and pre-industrial, above pre-industrial, and CO2 concentrations of 350 parts per million. Sadly, small amounts of warming, just 0.4 of a degree, has meant that ice sheets have quadrupled their mass loss in terms of sea level rise. Just 0.4 of a degree there. We're already committed to long-term sea level rise, even if climate warming is held to 1.5. I mean, you can see some of the scenarios if we were to hold global mean temperature to 2 or 3 degrees. However, what we're really worried about now as glaciologists and scientists studying ice sheets is that every increment of warming above present day increases the chances of crossing temperature thresholds that trigger instabilities that become irreversible, at least on human timescales. And I would say that the latest science that's emerging suggests that 1.5 should be seen as a guardrail. We don't know. These triggers, we may have already crossed them, actually, or it may be 1.6, it may be 1.7. But I think, we have to be ambitious here, and we have to aim for what is already sufficient to trigger these instabilities. And if you were to take this to its logical conclusion, that would be that actually if you want to protect ice sheets and stop sea level rise from ice sheets, the safe limit for ice sheets is 1 degree Celsius. And that was actually proposed back in the 1990s, and of course has largely been ignored. So I'm going to hand over now just to Kim Ross, who's going to say something from kind of some of the work that she does for Rethink Energy Florida about the impacts that are felt on the ground. Over to you, Kim.
Thank you. Thanks, Chris. Back home, it's 4 a.m. and I did put out the notice that this would be live streamed. And so I feel like if anybody was up at 4 a.m. watching this and watching Chris, they might not be going back to sleep. However, there is some good news, as you said at the end. And I want to talk to you just about 3 quick things. The first thing I'm going to mention is something that you mentioned in your talk about the matching of sea level rise with storm surge. The second one I want to talk about is sunny day flooding. And then I want to talk a little bit about some ideas about how to move forward and change things as we go forward. So I'm a co-founder of Rethink Energy Florida. We founded Rethink Energy Florida in 2010. Prior to that, the last major hurricanes to hit Florida were in 2005. And then we got into 2017 and 2018. 2017 with Irma. 2018 hit near my hometown of Tallahassee and Panama City. That was Hurricane Michael. And then we get into the 2020s, and we've got Ian. Of course, everybody remembers in 2022 hit Fort Myers. In 2023, Idalia hit right near again to our east of where I live. In the Perry area, and then most recently, Helene and Milton combined impacts. And I will tell you, when I first started Rethink Energy Florida, I heard someone talk about that combination of sea level rise plus storm surge, and that's where the danger is to Florida in the near term, and that really has come to pass. And I know you all have seen some of those images of houses floating away because of storm surge. We have a team that is actually in the field and does work with low-income communities, primarily in Tallahassee, but we've been in to our east in the Perry area, in some of the areas that are low-income and rural and have been impacted in major ways and aren't getting the funding and the attention that some of the larger cities are getting. And so we really see that as a major impact. The second thing I'll mention is sunny day flooding. Also, when I founded Rethink Energy Florida in 2010, there was nothing, sunny day flooding, this really wasn't well known. It might happen once a year. And now it is happening pretty much on a monthly basis in our Southeast Florida area. I went down there not too long ago because I had never seen sunny day flooding. I live in North Florida. I kind of live in an area where if there's sea level rise, maybe even I think we'll even be okay if the worst of the worst happens from a sea level rise perspective. However, I went down to Fort Lauderdale in that area just to see what it looked like. And what the one thing I walked away from an impression perspective is that they are just barely keeping it under control. Our state has put billions of dollars into pumps, into raising roads, those sorts of things, both at the state level and at the county level. And they are able to keep the water mostly out of the roads, at least to the point where people can still drive through them, as long as nothing else happens, as long as there's not a rainstorm on top of it. Rainstorm, not hurricane. Of course, as long as there's not a hurricane as well. And so these are the impacts that are very real and happening now in Florida. One of the things the final thing I just wanted to mention is that, we have been thinking about it from that perspective, as the fact that Florida is putting a lot of money into adapting to sea level rise. But for those of you who are familiar with our politics, not necessarily thinking about the root cause. And so we are talking about the idea of, in addition to 1.5 degrees Celsius, also making sure that people are aware of what that sea level rise limit really needs to be to keep the ice sheets slightly under control, more under control, so that Florida doesn't experience the worst of the worst, as you saw with the image that let me see if I can find that image. There you go. So with that image, this image, I'll leave you with this. This image, if we are going to go there, we're talking about managed retreat, right? I mean, we're talking about managed retreat of one of the largest cities in the United States. And at that point, you're probably actually not talking about managed voluntary retreat, but you're talking about forced retreat at that point, and all the justice implications that come out of requiring people to move, right? And there's all sorts of complications and things that you've got to look at when you're talking about how are we going to manage retreat and how are we going to move that. So I'm here. This is my first COP. And I'm here in part because I really think it's important to move forward in terms of an ambitious goal of 1.5 degrees and also, or 1 degrees, I like that, but I'll go with 1.5 degrees and also keeping in mind that sea level rise impacts and what that looks like and how many people are impacted by that. So I think that's all I have to say. Thank you so much. And thank you, Chris, for letting me speak for a couple of minutes here.
So I'm sure we're both happy to take questions for a couple of minutes now, if anybody has any questions. Yeah.
I have two questions that are kind of related. First one, is there any other types of thresholds in the cryosphere? So you see in the Amazon forest, we have obviously temperature, but also deforestation reduces that temperature threshold. Are there any other types of thresholds? And are there any balancing feedbacks within the cryosphere?
Oh, yeah.
To stay, you talk about a balance,
yeah.
but always with a positive feedback, yeah. There is a negative feedback to balance. That's how.
Yeah, yeah. So that's a good question. For those who are listening online, the question was, there were two questions. One is that, are there any other instabilities or feedbacks that could also see ice sheets contribute further to sea level rise? And the other part of the question, or the second question, was, are there any what we call negative feedbacks, things that will actually dampen down the change and tend towards stability? The feedbacks I talked about today are probably the three most commonly cited ones. There is some work as well suggesting that there may be some feedbacks to do with fresh water from the ice sheets making it into the oceans and changing ocean circulation patterns. And in some cases, that could enhance further melting of the ice sheet. But in other cases, so around the southern hemisphere in the Southern Ocean, of course, in other cases, it's been argued, at least by some, that you could get melting of the Greenland ice sheet might affect the Atlantic meridional overturning circulation, which is that kind of that North Atlantic process, and might lead to cooling. So if there are other feedbacks, they're mostly to do with ice-ocean interactions. I can point you to some key literature there, because they're probably quite complex to explain. In terms of negative feedbacks that would tend towards stability, I'm not really aware of any related to ice sheet mass loss. I mean, the process does work in the opposite direction. If you deglaciate an ice sheet and you have a land mass and then you start slowing on it and you slowly start to build ice, that reflects more incoming solar radiation, that will allow you to grow more ice, and it can work, but that process is much, much slower. So part of the problem that we're talking about today is that you can get rid of an ice sheet very, very quickly, within a matter of centuries. Some of the latest modeling shows that West Antarctic ice sheet could collapse in 200 or 300 years. But actually, if you want to regrow the West Antarctic ice sheet via those feedback processes, that probably takes several millennia. So we drop off, we lose mass very quickly, but to go back up, it takes a much longer time. Any other questions? Yeah.
First of all, I was impressed by the will of the speakers to share the information. Thank you very much.
Thank you.
And my question is, do we have at least approximately understanding how much the impact of mountainous glaciers on the rise of the sea level?
Yeah.
Thank you.
So the question for those online was, do we have an idea of the sea level contribution from mountain glaciers? And we do. Obviously, today's talk was very much focused on the ice sheets. So the ice sheets store almost 60 meters of sea level equivalent. So if you melt all the ice sheets in Greenland and Antarctica, it's about 60 meters. The mountain glaciers all over the world, there's about 275,000 of them, but their sea level equivalent volume is 32 centimeters. It's much smaller. But during the last century, the melting of mountain glaciers was the dominant contributor. What's happened just in the last few years is that the big ice sheets have overtaken them. But that's not to say, of course, that the loss of mountain glaciers isn't really important. It still adds to sea level, but it has other effects on river flow, on water resources, hydropower, agriculture. We increase the likelihood of hazards in these mountainous regions, glacier lake outburst floods. And they've been the topic and will be the topic of other talks in this pavilion. So stay tuned.
Thank you.
Any other questions? Okay, well, I'll hang around. I'm sure Kim will as well, if anybody wants to join any conversations. And thanks for your attention.